Our last lecture today is by Canary, who's going to talk to us about, he's going to give the first of a series of lectures about Kleinian groups and Sullivan's dictionary.
My mic on? Okay. So it's a great honor to be asked to speak at Dennis's birthday conference. You know, Dennis is, of course, someone who's had a big influence on both the fields I'm going to talk about, complex dynamics and Kleinian groups, and a big influence on my work and on, you know, anybody who's worked in the field. But he's also someone who had a sort of influence on me as a young mathematician. When I was a graduate student, we used to, some of us Thurston students used to go up to CUNY and visit Dennis's seminar, and, you know, we would listen to the seminar in the morning, and he would talk to us in the afternoon, and he would take us to lunch, and, you know, just the opportunity to observe, you know, how a great mathematician thought about mathematics had a big impact on me as a young mathematician. I remember one of the things Dennis has said that particularly had a big impact. He told me, when you're having 10 wrong proofs a day, then you know you're really onto something. And that's something I pass on to my own grad students, because I think there's a lot of truth there. You know, sometimes what you're onto is nonsense, but, you know, it's also true when you're onto something good. So I want to thank Dennis for what he did for me as a young mathematician. You know, and I was nervous when Misha asked me to give these talks, because I was supposed to give a talk about a dictionary between two languages, and I really only speak one of these languages. And I'm, you know, supposed to talk for 3 hours. But then I realized it was, you know, Dennis's conference, so I'd probably only have to speak for about an hour. So it really wouldn't be so bad. You know, and so I started to get calmer, and then, you know, I ran into Jeremy last night at the banquet, and he thought he would calm me down. So he says to me, so Dick, what do you know about rational maps? So that made me, so I went back to my room and spent another 3 hours on the talk. So, anyway, so, oops, does that work? No? Oop, pointing the wrong way. There we go. So what's the basic idea of the Sullivan Dictionary? Well, it provides a framework for thinking about problems in both rational maps and in Kleinian groups. And in some cases, you could actually take a proof and translate the proof using this dictionary into a proof in the other language. And that's not the most common case. Normally, it sort of provides some sort of looser analogies which suggest problems in areas of research and allows you to go back and forth between the fields and sort of at a little bit of a higher level. So what we're going to do in this mini course, we're going to start with sort of trying to say a little bit what the Sullivan Dictionary is, and hopefully people, if I say anything too nonsensical about rational maps, someone will point it out. And in particular focus on the quasiconformal deformation theory. And this is where the analogy is closest, where your major tool is quasiconformal maps and the measurable remapping theorem. And then what we're going to do is focus on sort of 3 big conjectures that were all proved in, let's say, the last 10 years. So we're take a trip back to the naughty aughties, right? Marden's tameness conjecture, Thurston's density conjecture, and the Bers-Sullivan-Thurston density. That's supposed to say Thurston's ending lamination conjecture, not Thurston's density conjecture. Okay, and all these. And so Ken Bromberg's going to give a talk on the proof of the density conjecture. Dan Gabai's going to give a talk on the proof of the tameness conjecture. And Yair Minsky's going to give a talk on the proof of the ending lamination conjecture. And I'm supposed to sort of be the setup guy for these talks. So I'm going to talk about the motivation and also talk about some of the applications of these. Okay, so, well, what is a rational map? It's just quotient of 2 polynomials. So just to keep something in mind, you know, something really silly, like R of z is z squared is a rational map. And then a Kleinian group is a discrete subgroup of PSL2C. And we're going to think of this as a group, first as a group of conformal automorphisms acting on the Riemann sphere, and then you can talk about the dynamics of that action, just like you talk about the dynamics of action of a rational map on the Riemann sphere. And so there's where the analogy is closest. the analogy starts slipping a little bit when you can also think of a Kleinian group as a group of orientation-preserving isometries of hyperbolic 3 space. And that's when it's a little bit harder to see how the pictures line up. So let's get a couple pictures in mind. One Kleinian group you might have in mind is you might take 4 disjoint circles, and then you might take one element taking that circle to that circle, and another element taking that circle to that circle, and you would take the group generated by those two. That's called a Schottky group, sort of the simplest, perhaps the simplest Kleinian group you could have in mind. And the other Kleinian group you might have just in the back of your head would be, you would take, first of all, a Fuchsian group. So that's supposed to be the unit disk. And then we would take, so we have over here a surface of genus 2, and we would cut it up into an octagon. And then we would build a regular hyperbolic octagon over here, which glued up. Oops. By 4 maps, and that's how you make, so the group generated by those 4 maps is a Fuchsian group. It acts on the unit disk, but it's just a group of conformal automorphisms. So instead of taking those octagon to itself, you imagine take that circle goes to that circle, and that circle. Where'd that one go? Oops, I had that circle go to that circle. This circle goes to this circle, et cetera, et cetera. Okay. So just a couple examples to have in mind. Wrong way. It's upside down again, isn't it? Okay. So what are the basic objects you would associate to this? You might, first of all, look at the action on the Riemann sphere, and you might ask yourself, where is the action interesting and where is it uninteresting? So for a rational map, you might say it's not so interesting if in some neighborhood of the point, the group of iterates, the collection of iterates is a normal family. So that's called the Fatou set, and the complement of the Fatou set is the Julia set. For a Kleinian group, you might ask yourself, it's not so interesting where the group action is properly discontinuous. So that means there's some neighborhood such that all but finally many elements take that neighborhood off itself, and the complement is called the limit set, and that's sort of where the interesting dynamics on the Riemann sphere happen. Oops, I forgot one thing to mention. Previous slide is I'm going to assume throughout this slide, if I don't say it, I mean it that the group is always going to be finally, Klein group is always going to be finally generated. It's always going to be torsion free, and it's always going to be non-abelian, because abelian Kleinian groups you can sort of say everything you want about them. There's nothing interesting. And then infinitely generated Kleinian groups, nothing's true about. So, as yet, yeah. Well, that's a lie. I mean, that's not even true now. But okay, so the engine that sort of runs the sort of most direct part of this dictionary is the language of Did I do everything last time? Is the language of quasi-conformal maps. I was going to say. So let's see actually over here. What is the Julia set over here? So the Julia set of z goes to z squared. It's just the circle, the unit circle. Off of the unit circle, either everything collapses to 0 or infinity, nothing interesting happens. On this Schottky group picture, then the limit set. If you look at sort of the keep iterating this picture, you see these go inside and these go inside. And you keep looking at the iterates, so you get a Cantor set picture. The limit set is a Cantor set. And for the Fuchsian group, the limit set is just, again, the unit circle. So just these very simple examples. OK, so I think Bruce told us all what a quasi-conformal map is. But let me sort of, in great generality, let me sort of just say it very simply. So we're going to, if you have an orientation-preserving homeomorphism with some amount of regularity, say absolutely continuous on lines, there's lots of ways of saying what kind of regularity you need, then you can define a Beltrami differential, which is just the derivative with respect to z divided by the derivative with respect to z bar. Is it the other way around? Oh, you're right, it is. Already. I can't even really claim that that's because that's a rational maps thing, can I? No. No, yeah, okay. You make a good point. Okay. Anyway, so we're going to think of this as an element of L infinity of the Riemann sphere, and a map is quasiconformal if this is almost everywhere less than 1. Okay. So the way I like to think about this, if in the case that it's differentiable, what happens is this unit circle goes to an ellipse. And what does this Beltrami differential measure? Well, it measures the eccentricity of this ellipse, and its angle keeps track of the axis keeps track of which direction the major axis of this ellipse is pointing. So the eccentricity is exactly that formula, and you can say that the preimage of the major axis makes an angle which is the argument of the Beltrami differential with the x-axis. So this is keeping track of your quasiconformal map is sort of stretching in some direction, and this keeps track of which direction it's stretching in and how much the stretch is. So, and we'll see that one of the things that comes up here is the key thing is if you look at this direction of stretch, that gives you an invariant line field. So, it gives you a line field. And yeah, so and if your Beltrami differential is equivariant with respect to some group action, then that line field will be invariant with respect to the group action. So the major tool in both of these fields is something called the measurable remapping theorem. Did you talk about that in your first talk, Bruce? Yeah, okay. So this is all review. It says that if you give me a Beltrami differential, then there's a unique quasi-conformal map up to post-composition with a conformal map. And this won't really matter for our talks, but this, the hard work is to show this quasi-conformal map depends analytically on the Beltrami differential. Okay, so a key observation here is that if you start with a Kleinian group and you have a Beltrami differential, which is equivariant with respect to that Kleinian group, then you can take the quasi-conformal map and you conjugate the group and you get a new Kleinian group. So the equivariance is, you can, of course, always conjugate a conformal map by a quasi-conformal map, and you get a quasi-conformal map. The equivariance of the Beltrami differential guarantees that that resulting conjugate is also a conformal map. So if we have an equivariant Beltrami differential, we get this new quasi-conformally conjugate Kleinian group, and we're also going to want to keep track a little bit more information there. We've quasi-conformally conjugated Kleinian group. We not only get a new Kleinian group, but we sort of have an identification of the new Kleinian group with the original Kleinian group. And then we can think of that as a representation of the original Kleinian group into PSL2C. So basically, you take rho of any element, and you take it to the appropriate conjugate element. Okay, similarly, if R is a rational map, and you have an equivariant Beltrami differential, and you can conjugate that rational map by the associated quasi-conformal map, and you get a rational map. Okay, and so probably the first big example of the Sullivan Dictionary was he gave a new proof of all fours finiteness theorem, which I'm stating a special case of here, and I'll state the general form in a minute. And he also proved that if you have a rational map, then its Fatou set has no wandering domains. Okay. So the all fours finiteness theorem in this case says that if I take a component of the domain of discontinuity for my Kleinian group, then there exists some non-trivial element of the group which takes that component to itself. And in the rational maps, you take a component of the Fatou set. The rational map preserves the Fatou set, so it takes a component to perhaps some other component to perhaps some other component. You keep going. Eventually, that's periodic. So you can sort of summarize both these results by saying that there are no wandering domains. Okay, so let's give a sort of sketch of these proofs. Well, suppose there was a wandering domain. Well, the basic idea then is then you would somehow have an infinite dimensional space of inequivalent Beltrami differentials. And so what might that mean? Suppose your domain was a Jordan domain. And you can, first, certainly there's an infinite dimensional space of Beltrami differentials. That's not so interesting, but inequivalent in the case when you had a Jordan domain would mean if you take this Beltrami differential and you take the associated quasiconformal map, it would do different things on the boundary. It would be a different map on the boundary Jordan curve. So that's what inequivalent means here. In general, you have to do things like talk about prime ends that are a little more complicated. Okay, you just have those Beltrami differentials just on D. How are we going to make an equivariant Beltrami differential which is supported on the entire Riemann sphere? Well, the first thing you do is you just take those Beltrami differentials on D, and you can transport them around the Riemann sphere by either the group or by the rational map. And then if any place that you don't hit by transporting that around, you just set the Beltrami differential equal to 0. And this gives you an equivariant Beltrami differential either on the domain as continuity, which is supported either on the domain as continuity or on the Fatou set, and you get an infinite dimensional space of inequivalent ones. The measurable Riemann mapping theorem allows you to, each of those Beltrami differentials, you associate a quasiconformal map, and so I get an infinite dimensional space of quasiconformal conjugations. So in the Kleinian groups case, you finish the proof by saying, well, that would mean I would have an infinite dimensional subspace of the space of representations of gamma into PSL2C. Well, but gamma is finitely generated, and the representation is determined by what you do to each generator. That's only a finite dimensional set of possibilities. Okay? And similarly, in the rational maps case, what you always get, if you start with a rational map of degree D, the D is really a topological thing. So if you conjugate it by a quasiconformal map, the degree doesn't change, and so you get an infinite dimensional space of rational maps of the same degree, which is impossible. Are we okay, Misha? That makes sense? We buy that? Okay, good. Okay. So if gamma is a Kleinian group, the natural thing you might do is you might look at the action on the domain of discontinuity. Okay. And that's a group of conformal automorphisms of a domain in the Riemann sphere. So you can form the quotient, and it's acting properly discontinuously, so it makes sense to form the quotient, and the quotient is naturally a Riemann surface. Okay, so you get a Riemann surface associated to your Kleinian group. Now, if you're like me and you prefer instead to think of hyperbolic surfaces instead of Riemann surfaces, you notice that if you have a domain in the Riemann sphere, at least if its complement is more than a couple points, then that it admits a unique hyperbolic metric, a unique metric of constant curvature -1. That metric is invariant by conformal automorphisms of the domain, and so it's invariant by the group gamma, and the quotient is a hyperbolic surface. Okay. So all-force fineness theorem in general tells you that if gamma is finally generated, the conformable boundary is a finite type Riemann surface. Or equivalently, if you take this Poincare metric, it has finite area. And the proof really is just what we said here. If we had some domain, and if the quotient is infinite dimensional, if the quotient does not, it has infinite area, that allows me to construct an infinite dimensional space of deformations of the quotient surface. Any infinite Riemann surface has an infinite dimensional quasiconformal deformation space. And you can lift those quasiconformal deformations to quasiconformal deformations on this domain, and hence Beltrami differentials support on this domain, and do the whole same thing over again. So it's really the same proof. Okay. Oops. So you can think about this Riemann sphere as sort of a conformal boardification of your hyperbolic manifold. So your hyperbolic manifold is the quotient of the action on hyperbolic 3 space. And you can just think of just appending the Frobenius continuity there and taking the quotient. So this is a manifold with boundary where the interior admits a complete hyperbolic metric and the boundary admits the structure of a Riemann surface. And they're compatible in some sense. So let's think about what happens in these two cases. Well, if you think about this Fuchsian group, the domain discontinuity is the unit disk and the complement of the unit disk. The quotient of the unit disk is just going to be a surface of genus 2 in this case, and the complement of the outside of the unit disk is also a surface of genus 2 with the opposite orientation. In fact, it's the complex conjugate of this surface of genus 2. And so your manifold is topologically a surface cross I, and you have a conformal structure X here, and a conformal structure X bar down below. Okay? What happens in the case of the Schottky group? Well, you can look at the action on the Riemann sphere, and a fundamental domain for that action is the complement of those four circles, right? And you have your fundamental domain is the complement of those four circles, and so topologically, that's just a 4 times punctured sphere. One boundary component is identified with one boundary component. This boundary component is identified with that one, and the quotient is a surface of genus 2. Maybe I should have asked for more board. And what is the associated manifold? Well, a fundamental domain for this group action on H3 is you take those circles and you extend them to hemispheres, and you take everything above those 4 hemispheres. So what do you have? You have sort of a picture. If you take the sphere, you have this ball, and you've eaten 4 chunks out of the ball. And when you've eaten those 4 chunks, you've glued the boundary of one chunk to the other, the boundary of the other chunk to the other. Well, taking a bite out is topologically equivalent to pushing out is equivalent to pushing in, right, topologically. So topologically, this is like gluing a 1 handle here. This is like gluing a 1 handle here. And so what you get is a solid surface of genus 2, or a handle body. Okay? Am I drawing in all the wrong places, Josh?
That's fine. Do you want just one projector?
Can people see? Can everybody just see this one if I take one up and have a little more boardroom? Okay, yeah, take one up. I can't. I thought I was just going to talk today and not draw, but I can't help myself. Okay. So the nicest situation, notice that in both these situations, something really nice happened. This conformal boardification was actually a compactification, right? So from a topological viewpoint, that's sort of what you hope is going to happen. And so when that does happen, you're going to call, well, either the Kleinian group or the hyperbolic 3 manifold, you can translate this language back and forth, is called convex co-compact. And so now if we want to sort of put this into the dictionary and have a corresponding dictionary over in rational maps, we're going to run into a little bit of trouble because we don't know what the equivalent of the quotient hyperbolic 3 manifold is. But there's a million equivalent definitions of convex co-compactness, and this one is due to Dennis. It says you're convex co-compact if and only if you're hyperbolic on the limit set, which means that every point in the limit set, there's some group element which is expanding at that point. And in the setting of is there a question? Okay. And in the setting of complex dynamics, the analog is the class of hyperbolic rational maps, which are maps which are expanding on the limit set. So at every point in the limit set, some expansion. Okay. No one's giving me a funny look yet. Okay. Oops. So this sort of, we're going to talk more about Marden's tameness conjecture tomorrow, but it sort of gives me a chance to just say what Marden's tameness conjecture is. Notice that well, just as a definition, a manifold is topologically tame if it is homeomorphic to the interior of a compact three-manifold. And this is what we think every open three-manifold looks like secretly in the back of our heads, right? I mean, unless we're, geometric topology types, this is the only open three-manifolds we imagine, right? At least the ones with finely generated fundamental group. We can obviously just take infinitely many handles. That's easy to imagine. But in fact, not all three-manifolds with finely generated fundamental groups are topologically tame. But Marden's tameness conjecture predicts that hyperbolic three-manifolds are much more polite than average topological three-manifolds. And in fact, if they have finely generated fundamental group, they are topologically tame. They're just homeomorphic to the interior of a compact three-manifold. And Marden sort of was one of the first people to really start thinking about hyperbolic three-manifolds and Kleinian groups sort of with the tools of hyperbolic three-manifolds, starting to apply Dane's lemma and the loop theorem and Waldhausen's theorem. And he started asking all these sort of deep topological questions. If you go back to this paper from 1970, was published in 1974, but I think it was written much earlier, like 1971, you see he starts asking a lot of prescient questions like, is a hyperbolic three-manifold topologically tame? Which turned out to be a really central conjecture in the field, and I think there really wasn't any reason for him to think that would be important at the time. He also asked questions like, is there a characterization of which three manifolds might arise as quotients of Kleinian groups? So he's starting to ask real topological questions, so sort of a great paper. So one of the things he notices is that if you're convex co-compact, then you're topologically tame. Now, his definition was not my definition. So with my definition, this doesn't seem like much to notice. I mean, his definition was that you have a finite-sided fundamental polyhedra and no parabolics, I think. But he also proved several are equivalent. Okay. So that's Marden's tameness conjecture. And it turns out that this has a lot of consequences for the geometry and dynamics of hyperbolic three-manifolds. In particular, it's closely related to all-fours measure conjecture. And things like the ergodicity of the G-sig flow and all sorts of things like this. We'll talk about that tomorrow. Okay. So let's start trying to sort of systematize a little bit this quasiconformal deformation theory. So it's natural, if you start with a Kleinian group, to ask yourself the question, what is the set of all Kleinian groups quasiconformally conjugate to that group look like? Okay? And like I said, a quasiconformal conjugation not only gives you a new Kleinian group, but an identification of your new Kleinian group with an old group, of your original group. So that's why we use the language of representations. So we say a representation is quasiconformally conjugate if it arises just by conjugating the original group by some quasiconformal map. And now we can look at the space of all the representations quasiconformally conjugate to gamma, and that naturally sits inside what's called the character variety. So one of the things we're always going to do is we don't care to distinguish between two Kleinian groups which are actually conformally conjugate. So we're always going to mod out by PSL2C acting by conjugation, and the character variety is just the full set of representations of the group into PSL2C, modded out by PSL2C. The double slashes are not actually a typo in this case, but that means that you're doing something, goes under various names. For instance, the Mumford quotient, such that the quotient actually is a variety. So you do some collapsing just at the reducible representations, which really won't be of much interest to us. Okay. And the first thing you sort of might ask yourself is, like, if you start with a Kleinian group, are all nearby Kleinian groups quasiconformally conjugate to you? Right, it's a sort of basic sort of dynamical question. You might ask yourself, suppose you have any old dynamical system and you have a nearby dynamical system in whatever sense you might mean, are those two dynamical systems conjugate? Okay. So Marden, in the same paper, showed that if your group is convex co-compact, then this Kleinian group is quasiconformally stable, which means that this this set of quasiconformal representations, quasiconformally conjugate representations, forms an open neighborhood of the inclusion map. Okay, and there's sort of a basic sketch which goes here, and let's think about it sort of mostly sort of in the two-dimensional case. So if you take something convex co-compact, I said there was lots of criteria, and one of the criterion is that your fundamental domain is finite-sided and there's no cusps. So you start with this fundamental domain, and if so this element goes to that goes to that goes whatever. I think I have 7 here, don't I? That's not going to anyway. 2, 3, 4, 5, 6, 7, 8. So you have something like that. If you start with a Kleinian group, and now suppose I wiggle the Kleinian group just a little bit. Well, then if I take sort of this side, the image of that side is going to wiggle just a little bit, and the whole picture wiggles just a little bit. Right? So, assuming that my fundamental polyhedra was sort of in general position in some sense, if I wiggle the gluings a little bit, I can wiggle the polyhedron a little bit, and I get a new fundamental polyhedron for my new group, which is combinatorially the same as the fundamental polyhedron for this group I started with. Okay? So now, if you notice that implies that since your manifold is obtained by just gluing up the fundamental polyhedron, that implies that your manifolds are in fact homeomorphic. Well, but these finite-sided polyhedra are pretty easy to understand. So once you know they're homeomorphic, it's not so hard to check that they're in fact bi-Lipschitz homeomorphic. You can just upgrade that map to a bi-Lipschitz homeomorphism. This isn't the language that Marden uses. He used the language of quasiconformal maps entirely, but this is sort of going to be in keeping with some of the other things that happened during this mini course. So I'm updating the proof here. So if you take that bi-Lipschitz homeomorphism between the quotient maps, it lifts to a bi-Lipschitz map from H3 to H3. And in Bruce's talk, I'm sure in the first talk, you must have said that bi-Lipschitz maps of a hyperbolic metric space extend to quasiconformal maps of the boundary. Right? So this is a bi-Lipschitz map which conjugates gamma to rho of gamma. And then when you lift that up to H3 and you extend it to a quasiconformal map on the boundary of H3, that gives you a quasiconformal map conjugating gamma to rho of gamma. And we're done. Okay. So, so from a dynamical viewpoint, these convex co-compact things are stable. Okay. So you might extend. Did I do something wrong?
Finite-sided fundamental domains are infinite.
Yeah.
So that continuity wiggling argument only works on a compact set, doesn't it?
Well, but if it's convex co-compact, they're never tangent at the boundary. So if they were tangent at the boundary, that might
do more argument there, right?
Yeah, I'm not being. Yeah, this is a sketch. But let's think about this case here. Let's think about the Schottky group case. The point is that you really have trouble if there are cusps. If there are cusps, there are two sides which are tangent at infinity. If you're in the convex co-compact case, then it's more like the Schottky group case. So if I take this, say this gets paired to this, and if I change this representation a little bit, what does that mean? This circle moves just a little bit. So it's really, in that case, it is in some sense happening on a compact set, and that compact set is H3 union the Riemann sphere. And if you don't have to worry about tangency, then it really is okay. So, yeah, I was trying to lie even more than I should probably, though. So you might, there's sort of a more general notion of stability, which is called structural stability, which says, does there exist an open neighborhood of the representation so that every nearby representation is injective? So this is a much, this is a weaker notion than being quasi-conformally stable. And one of the things we see right away then is that convex co-compact Kleinian groups in particular are structurally stable. If you wiggle a convex co-compact Kleinian group, you get a convex co-compact Kleinian group, and the representation stays injective. So Dennis sort of showed the other direction, which says that if you start with a finitely generated Kleinian group, and you know that all you know is that if you wiggle it a little bit, it stays injective. So if you take a representation near to the inclusion map, it's injective, then that's enough to guarantee it's convex co-compact. Okay, and so this proof, I don't think I can give an honest sketch except in the time I have, except for people who already know what some of the words are. So let me sketch it for the people who know what the words are. If you don't know what the words are, I'll try to get back a little bit more down to earth on the next slide. But the basic idea is, suppose you have an open neighborhood consisting of injective representations. Well, then you use the lambda lemma to show that if you have a sort of homeomorphically varying one-parameter family of faithful representations, then you can sort of look at the fixed points of the hyperbolic elements. Those vary holomorphically, and so that gives you a quasiconformal variation supported on the limit set. You apply All-Force Spinous theorem, and you piece them together to show that if you have this holomorphically varying family of injective representations, they're all quasiconformally conjugate. Okay? Now, you use the fact that X gamma is an algebraic variety, and in fact, even more so, it's known that if your representation is discrete and faithful, it's not only a point in the variety, it's a smooth point. So we don't even have to worry about singularities here if we don't want to. Then every nearby representation lies in some holomorphic disk of representations. So what that says is that every nearby representation is quasiconformally conjugate. Okay, so that says that the quasiconformal deformation space has the same dimension as the character variety. And but we're going to see the next few slides, we're going to start seeing that the quasiconformal deformation space is just some quotient of the Teichmuller space of the conformal boundary. So how big the quasiconformal deformation space, or the dimension of the quasiconformal deformation space, is related to the topology of the conformal boundary. And here, this proof makes key use of Sullivan's rigidity theorem, which says that there's no invariant line field supported on the limit set of a finitely generated Kleinian group. So the no invariant line field thing, which is known in the context of Kleinian groups, but not in the context of rational maps, is really key here. And there's you can calculate the dimension of the character variety at this point. This is due to Thurston. And if you look at that calculation, you conclude that your manifold couldn't have any cusps, and that the Euler characteristic of the conformal boundary is twice the Euler characteristic of the group. And then this will make a little more sense tomorrow if you don't know what these, after tomorrow, if you don't know what these words mean. Then you check that all the ends of n must be convex co-compact. It means that if you go out in any direction, you must bump into the conformal boundary, and so that this conformal boardification is indeed a compactification. So I tried to figure out how I could say this all smoothly, but I decided just to put for experts there and then move on. So let me say a little bit about what's happening over on the rational map side of the dictionary here. Well, you can say a rational map is structurally stable if all nearby rational maps are topologically conjugate. Okay? And in the rational map setting, what was known in the early 80s, Magnier, and Sullivan proved that the set of structurally stable rational maps is open and dense. So we're going to see in a minute that the analog of that conjecture is was one of the key open conjectures in Kleinian groups for 25 years after this time. On the other hand, the analog of knowing that once you're structurally stable, you're convex co-compact is still not known in rational maps. And this is a major conjecture in the area, and it's known, I guess, in some cases. If I say any more, I'll get myself in trouble. But this is a big conjecture that knowing structural stability is enough to guarantee hyperbolicity. And it was observed back in the paper that the key missing ingredient there is exactly that there's no invariant line field supported on the Julia set, or sort of no Beltrami differential supported on the Julia set. Invariant. Okay. And so in Kleinian groups, the major conjecture is there's all these. I wrote it down. The basic idea is that every finitely generated Kleinian group is a limit of convex co-compact Kleinian groups. But that's just false because your Kleinian group might have these Z plus Z subgroups. But if you don't have any Z plus Z subgroups, that's just the conjecture that every Kleinian group is a limit of convex co-compact Kleinian groups. In general, if you do have one of these Z plus Z subgroups, then you say, well, you're a limit of as close as you can be to convex co-compact, which means you're geometrically finite, and the only parabolic elements you have lie in these Z plus Z subgroups. So geometrically finite, there's various definitions, one of which is that you have a finite side fundamental polyhedron. Okay. Tomorrow, when we do convex core, a better definition is that your fundamental group is finitely generated and your convex core is finite-sided. That's a better definition because that's a definition which generalizes well to higher dimensions. So this is the conjecture Ken's going to talk about. And I'm going to sort of, depending on whether I run out of time, I'm going to circle back to this conjecture and state it from a slightly more sophisticated, a different viewpoint. I don't know if it's more sophisticated or not. Okay. So something I promised you in that sketch is this so-called quasiconformal parameterization theorem. So there's a lot of people who have been involved in the statement I have on here. I think the basic idea of these sorts of statements is due to Bers, going back to Bers' simultaneous uniformization. And to prove it in the most general setting where you just assume it's finally generated, you need to use the Sullivan rigidity theorem. So it's most simply stated, and I'm going to sketch the proof in this case, that if you start with a freely indecomposable Kleinian group, that just means you can't write the Kleinian group as a free product of one group and another group. Well, unless one of the groups is trivial, which you can always do. Or if you prefer, a more general statement, where this is also true, is that every component of the domain of discontinuity is simply connected. So for instance, that's going to work just fine for our Fuchsian group, but for our Schottky group, it doesn't work at all because there's only one component of the domain of discontinuity, and it's a complement of a Cantor set. So very non-simply connected. So I'm not sure. Do I need to say what the Teichner space is here? Have we said that already? I just got here yesterday late. What? Okay. So basically, when you think about a Teichner space, I'll get my little fish. What's it? So let's assume that, so this case is the Teichner space of a possibly disconnected surface, but that's just the product of the Teichner spaces of the components. So what's the Teichner space? You have sitting over here a naked topological surface, say F. This is just a topological surface. It doesn't know what to do with itself. It's perhaps a little embarrassed about being naked at such a large public lecture. And did any of the other speakers have that dream last night? And then you have this hyperbolic clothing. So this is X is a hyperbolic surface. And then you have an orientation-preserving homeomorphism. So that's an element of Teichner space. It's a hyperbolic surface, which we think of as clothing for our naked surface, and an orientation-preserving homeomorphism, which we think of as a way to wear that clothing, as instructions to wear that clothing. And when we have instructions to wear that clothing, we're mathematicians, so if we're a little askew, we don't care. Our instructions are only defined up to isotopy. But even for a mathematician, it's bad if you come to work and your head is through the armhole. So that's a non-isotopic thing. It's up to isotopy. the Teichmuller space of F is the set of pairs X and H. X is a hyperbolic surface. And then H from F to X is an orientation-preserving homeomorphism. And this is up to isometry. So what does that mean? That means that if I have two pieces of clothing, then I have an isometry here, and it's up to isotopy, which it means that J is homotopic to H2 compose H1 inverse. That's the equivalence relation. Okay. Now, in general, if you start with a general Kleinian group, like a Schottky group, say, in our picture there, it's some quotient of Teichmuller space by a subset of the mapping class group. It's a torsion phi subgroup, so it's always a manifold, but that subgroup can be infinitely generated. So for instance, in the Schottky group, so this is the group of isotopy classes of homeomorphisms of the conformal boundary, which extend to homeomorphisms of the entire manifold, which are homotopic to the identity. So you might think that sounds very trivial, but if you think about the handle body, there's a Dane twist. So I take a curve which bounds a disk, I can Dane twist about it, which means I take the handle body, cut along the disk, twist one of the sides, and glue it back together. So that gives me a homeomorphism on the surface. It's certainly homotopic to identity. It does nothing in the fundamental group, but up to isotopy on the boundary, it's up to isotopy is distinct from the identity. So, for instance, for a handle body, this group is generated by these maps. In fact, it's always generated by such maps, and it's typically infinitely generated. So that's bad. Okay, but let's give a sketch of the proof. It's sort of ignoring this issue. So what's the basic idea? You start with your quasiconformally conjugate representation, and that gives you your new manifold, which is n sub rho, and it has a new conformal boundary, which is the quotient of its domain discontinuity by the new group action. And there's a quasiconformal map doing the conjugation. But that map takes the domain of discontinuity for the old group just to the domain of discontinuity of the new group. And so it descends to a homeomorphism from the old conformal boundary to the new conformal boundary. So what is that? So what do we have? We have exactly a point in Teichmuller space, right? To a quasiconformally conjugate Kleinian group, we associate a new hyperbolic surface, which is its conformal boundary, and the orientation-preserving homeomorphism just comes from the quasiconformal conjugacy. Okay, and this is where for truth in advertising, this is where we're using the freely indecomposable assumption, because this is not well defined in general. So why is this surjective? Well, this is the measurable remapping theorem. So if you take some new point, as you take some point in the Teichmuller space, well, that's a new surface, and it's a quasiconformal map from the original conformal boundary to some new abstract surface. And we want to make that new abstract surface be a conformal boundary. So we have the surface. So, yeah, what's the picture here? So suppose we start with a Fuchsian group. We start with a Fuchsian group, and it's originally x and x bar, and now I picked two new surfaces, and I took a conformal structure y on top and a conformal structure z on the bottom, and I want to somehow fill in a hyperbolic 3 manifold. All I have is the surface. Well, I have a quasiconformal map from x union x bar to the surface, and that quasiconformal map is the map between Riemann surfaces. The Beltrami differential makes sense because it's just keeping track of the stretch. Right? It doesn't need to be a map from the Riemann sphere to the Riemann sphere. That gives us a Beltrami differential, and the Beltrami differential is invariant with respect to the group action because it's just the lift of a quasiconformal map on the quotient. And, well, so now we get a Beltrami differential supported on the domain discontinuity. So we just set it equal to 0 in the limit set. We don't care. produce a quasiconformal map, and that since the Beltrami differential was equivariant, when we conjugate by this new quasiconformal map, we get a Kleinian group, and we just check that the quotient of the domain discontinuity by this new Kleinian group is the surface X we started with. It's just formalism, really. If you just run through the definitions, it just falls right out. So that tells you that this map I constructed is surjective. Every conformal structure arises. Once I give you Y and Z, I can fill in with a hyperbolic three-manifold interpolated between them. Okay, now why is it injective? Well, suppose you have two representations, row 1 and row 2, and they have the same conformal boundary. Well, that means when you look at the point of these conjugations, that gives you these maps phi2 bar and phi1 bar, and then phi2 bar composed phi1 bar inverse is homotopic to a conformal map. So just isotop them so that they are a conformal map. So I could just assume that phi2 composed phi1 inverse is conformal on the domain of discontinuity. So the setting in which Bers worked was the geometrically finite or convex co-compact setting. And if gamma is convex co-compact, Alfors had proved back in the 60s, and I'll give you his proof tomorrow, that the limit set has measure 0. So this is a Beltrami differential sits in L infinity. What happens on a measure of 0 doesn't matter. So that says that if you're conformal on the entire Riemann sphere, if you're conformal on the domain of continuity, in fact, you're conformal on the entire Riemann sphere, and in fact, these two things are just conjugate. These two representations are just conjugate to one another. Okay, but in general, we didn't know at the time that if you're a finely generated Kleinian group, then your limit set has measure 0. Well, or is everything. We'll talk about that tomorrow. But what Dennis proved is that when it's finally generated, there's no Beltrami differential support on the limit set. So that's like, Alfors measure conjecture says either your limit set is everything or it has measure 0. And why do you want to know that? You want to know that exactly to show that there's no Beltrami differential support on the limit set. That's the whole motivation. So, I mean, in some sense, before we do Alfors measure conjecture, we knew, because of Sullivan's rigidity theorem, all the real consequences of Alfors measure conjecture. So you know that you've got this quasiconformal map. It's conformal on the domain of discontinuity, which means its Beltrami differential is trivial on the domain of discontinuity. But then Sullivan's rigidity theorem tells you the Beltrami differential is also trivial on the limit set, so it's trivial everywhere. Again, it's a conformal map, and they're conjugate.
Can I make a comment?
Yeah.
So, I mean, in '78, I think I worked for a very long time to try to study this Alfors measure problem and reduce it to an ergodic theory problem. And I went through all the way to proving ergodicity, and I finally could prove to myself, after about a year, that I could not prove it. I had enough information about the question I could prove I couldn't prove it. There wasn't enough information, and it was kind of sad. Then I noticed the next day that it actually proved this. I mean, there was enough information to prove there was no like this.
Right, which is all you needed. Right, yeah.
And I didn't really know that was the motivation of the question either.
I don't know for sure. I always assumed, though.
No, I
don't know.
It is. I found out later.
Okay. Okay, so I actually ended up drawing the special case on the board, but the special case is this case of Fuchsian groups, which is that it says roughly in the case where your group starts out being Fuchsian, it says your domain of continuity is two surfaces, and it says that you can choose any two conformal structures on those surfaces, and you can fill it in with a hyperbolic three-manifold, and moreover, there's only one way to fill it in. Right? Once you know what the surfaces are, you know what the hyperbolic manifold is, which is, this is sort of amazing. The sort of the complex analysis in infinity determines everything. And yeah, so we're sort of heading towards the ending lamination conjecture, which I probably won't state today. Okay. So let me just get a little more language into play, because this will set up Ken's talk. And we'll also sort of give us a little sort of broader picture on these things. So a more topological viewpoint, perhaps, is you start with a compact, orientable, atoroidal, three-manifold. For example, just a surface cross I. All those conditions just mean its interior admits a hyperbolic structure. Well, post-Perelman. That's what. Actually, when you have non-empty boundary, Thurston had already proved that. So think of you have a compact three-manifold. Its interior admits a hyperbolic structure. That's what we know. And then we're going to take the space of all discrete faithful representations into PSL2C. Okay? And if you have a discrete faithful representation, what does that give you? That gives you a hyperbolic three-manifold because you're quotienting out by the image of the representation. But it gives you more information because the representation gives you an identification of the fundamental group of M with the fundamental group of your hyperbolic three-manifold. Well, these are k pi 1, so such a representation gives you a homotopy equivalence. All right? So now so this is, in some sense, the natural analog of Teichmuller. It's one natural analog of Teichmuller space. The difference in surfaces is that if you have two closed surfaces and you know they're homotopy equivalent, then you also know they're homeomorphic. This is not true for three manifolds, and I'll hopefully give an example at some point in these talks if I get there. So that's why homotopy equivalence naturally replaces homeomorphism here. And also, if you want this to sit someplace naturally and give it a topology and natural structure, it again sits inside the carriage variety, which is the space of all conjugacy classes of representations into PSL2C. And that's again, this is an algebraic variety. And we're going to think of this subset H of M as the space of marked hyperbolic three-manifolds homotopy equivalent to M. Another reason you want homotopy equivalence, you might say, I'm just going to chop AH up into pieces by homeomorphism type. The problem is homeomorphism type is not locally constant on AH of M. So that means chopping AH of M up by homeomorphism type is not really a natural thing to do. So if we rephrase the combination of the theorems of Marden and Sullivan we stated earlier, says the interior consists exactly of convex co-compact representations. Okay? And then if we rephrase the density conjecture, it tells you that the space of discrete faithful representations is the closure of its interior. Doesn't that make it sound more interesting? Anyway, and we know the interior of the nice convex co-compact representation says that every representation is the interior of a convex co-compact. Oh, I forgot an assumption. I'm going to always assume that M has no tori in its boundary. Again, if you have tori in its boundary, you always have to worry about these E plus C subgroups. I don't want to think about that. So I'm always assuming that M has no toroidal boundary components. It's time to stop, right?
Yeah.
Okay. Okay. So, yeah, I'm going to go over this more in the third talk, I think. But let me just tell you what you get in the end. You put all this information together, you get a parameterization theorem for the interior, which is sort of like the picture for the Mandelbrot set you should think about. To come back to our dictionary, that there's lots of components of the interior. There's one component for each marked homeomorphism type. Okay? And each component is parameterized by analytic data, the Teichmuller space of the conformal boundary. And this is true, again, if your fundamental group is freely indecomposable, or equivalently, you don't have, if you take a curve in the boundary of the three-manifold, if you can't shrink it to a point in the boundary of the three-manifold, you can't shrink it to a point in the manifold. So that's why it's sometimes called incompressible boundary. And there's a general, So if you make the assumptions I've made, there's only finitely many homeomorphism types, and each of these is a ball. So the interior is a bunch of balls. That's pretty nice, just sort of like the Mandelbrot set. Except, well, there's infinitely many there. In general, well, things get a little worse. If you allow pi1 of m to be the free product of two different groups, well, you still get one component for each marked homeomorphism type, and you still get each component is a manifold, and it's a quotient of type in their space. But there's sort of some bad news here, which is once you go into this world, typically there's infinitely many marked homeomorphism types. So there's infinitely many components. Maybe this doesn't bother you if you're used to the Mandelbrot set. And moreover, each of those components has an infinitely generated fundamental group. And you can make typically into a theorem like unless blah, blah, blah occurs. Okay. And so the ending lamination conjecture, so this is in some sense a complete picture of classification of elements in the interior, a complete classification of convex compact hyperbolic three manifolds in terms of topological and geometric data. And the ending lamination conjecture of Thurston, which Yair is going to talk about and I'll talk about a little bit, is a complete conjectural classification of all the points of AH in terms of topological data and asymptotic geometric data. Okay, I'll stop there.
Questions or comments?
What's an example of the homeomorphism type changes?
Oh, yeah. I would probably do that in my third talk. But basically, what? Yeah. So, but the basic, yeah. What's the basic picture? Okay. So if you take, here's my manifold, here's a 2 complex. I take a tin can and I insert a disk with 1 handle, 2, 3, 4. Okay, so that's a 2 complex is embedded in R3, thicken it up, and you get a 3 manifold.
The space between the
Right, yeah. So you have
like 3 rooms.
yeah, you have, what are the boundary? Like you have a boundary component of genus 5, of genus 3, of genus 5, and of genus 7. So there's 4 boundary components, 1 around the outside. And now here's a homotopy equivalent one. I take 1 on top, then I do 1 with 3, then I do 2, then I do 4. So, you know, the boundary components have genus 4, 5, and 6. So those are clearly homotopy equivalent because if you take these two complexes and you collapse the annulus, they're homeomorphic. Okay? So it turns out that you can take a sequence of manifolds with this homeomorphism type, and the limit has that homeomorphism type. And the basic idea is you take this tin can, you drill out the core curve here to make a cusp hyperbolic 3 manifold. You immerse this guy into this guy in a funny way, and then hit it with Dane surgery, and look at hit it with Thurston's hyperbolic Dane surgery, and hit it with the look at the hyperbolic Dane surgery, and that gives rise to a sequence of representations of this group where it magically changes homeomorphism type in the limit in some evidence. Anyway, in the 2-minute version.
More questions? Okay, so let us thank the speaker.